So, good day students, and welcome to the homework session for the second nugget in the lesson dealing with biofuels. I mentioned in the theory session that there are some, let me call them natural, markets for milled and compacted biofuels. What we found was that these two markets are at each end of the size span, so that the most costly fuels, pellets, might find their main market in the small-scale segment, and milled fuels would find their main use in the large scale. But then the milled fuels may also be pellets. The basis for the reasoning in the theory session was money. In a general course like this, aimed at a worldwide audience and intended to be more or less time independent, is any mentioning of money completely meaningless. However, costs are of interest. But the word cost, when I use it, is the thermodynamic cost. You will understand that better after this nugget. In case I would like to mention money, I would use the word expenses. So the main thing with this homework is to estimate the cost of compaction. Once you have finished this nugget, you will understand the aims and the cost of physical treatment of biomass. And you will also have some references to the cost for pelletization. This will give you a basis to stand on when we continue by looking at other conversion processes further on in this lesson. In the theory session, you were referred to 3 papers, all 3 concerned with the pelletization process as such. These papers will have introduced you to the basics of the pelletization process and to how different raw materials may behave in the process. So you are well aware that pelletization may be used for a variety of feedstocks, not only biomass and, to be more specific, not only for wood. In case you want to go deeper into pelletization, there are just any number of papers and reports available on the web. But for this session, I will want you first to download and read the doctoral dissertation by Frodesson. Scan through the dissertation first, but then study the section about the pelletization process, pages 7 through 12 in detail. You will find the link among the external link with this nugget. From the reading you did in the theory session and from this dissertation, you will be aware that the details of bonding in pellets is still not fully understood. And you will have realized that the process is complicated because of the complex structure of biomass as such. You may also want to scan the publications concerning the international market for wood pellets as covered by a number of publications at the IEA. We have now determined that the details of the pelletization process are really not well understood. And we have determined that the world trade of wood pellets is big and growing. And then you may have heard from people who are not working in the energy sector that the total energy required to produce pellet is as big, some even claim it's bigger, than the energy actually contained in the pellet itself. I still hear that quite frequently. But then the international pellet market has grown steadily for the last decades. So it is obvious that if pellets were not a profitable product, this market expansion would not be at hand. So let us do a simple estimate to see what is true. The figure in this slide is a copy of figure 4 from Frodesson's thesis. If you compare this figure to figure 1 in the paper by Henriksen and co-authors, you will notice that Frodesson has added the conical inlet section. So Frodesson separates the process into 3 steps. And let us now look a little bit closer to what might happen. For the first stage, it is assumed that the porous material undergoes an elastic compression, followed by the physical breaking of the cell walls. The cellular structure is broken and the material reoriented into a thin layer of, basically, cell wall fragments. As the material is pressed down into the conical inlet section, will it be compressed along its axis and also around the symmetry axis. But since the walls are sloping, will the compression occur differently as a function of height. So in this part of the compression, will the material be subject to many different forces, and it will be squeezed and torn into different shapes and sizes during its passage. But by the end of the day, once it enters the cylindrical part of the die, will it have been compressed but may well have retained its original shape, though smaller. So this is called redundant work. Starting like with a square cross-section and ending with a square cross-section, may the material nevertheless have undergone severe deformation on the way. Once the material enters the cylindrical section of the die, the active section, it is heated by the friction of the walls. The heat softens lignin and other agents that may serve as a binder, a glue if you wish, and makes this binder penetrate the structure. There is no further deformation in this stage, but the axial pressure is maintained by the friction forces. So now the material is glued together. The length and the diameter of the cylindrical part of the die will have a pronounced influence on the final pellet quality, since they determine the friction and the time. So let us now see if we can draw any conclusions from this. The first thing we assumed to happen was the crushing of the cell walls. The diagram in the slide illustrates the rupture strength of Scots pine, Pinus sylvestris, at 10% moisture quotient. You will remember that the moisture quotient is the moisture content on a dry basis. So the moisture content, as we generally refer to it, the wet basis, is a bit lower, about 8%. The x-axis in the diagram is the angle between the applied force and the wood fibers. The diagram covers 3 different load cases: axial tension, static bending, and compression. To generalize, one can say that the starting point for the 3 curves, the intersection with the y-axis, will be reduced to about half if the moisture content is raised to the fiber saturation point. Fiber saturation is about 22% moisture on a wet basis. The values at the right-hand side of the diagram, loads perpendicular to fibers, will not change significantly with moisture content. The diagram is copied from a classical Swedish material handbook, and I use it not because it is the most accurate, but because it contains lots of information and I had it available in my bookshelf. So what can be said from this is that if we want to crush the cell structure, we will have to apply a pressure exceeding 50 megapascal. The fibrous particles will be oriented at random. So now go back to the paper by Henriksen and co-authors and scan section 5, which is concerned with the structure of wood. As you will see there, may the particles well have a pronounced fibrous structure. And with the random orientation, will some particles be crushed at 50 megapascals, while others may just be slightly bent. But we can be pretty sure to destroy a major part of the cell structure. So what happens is that we have to apply a force to give a pressure exceeding 50 megapascals. In most practical situations is a slightly higher pressure applied, and as a normal value is often 700 bar mentioned. So that is 70 megapascal. But let us use 50 for our estimates. To estimate the force, I use the diameter for the active cylindrical part of the die. So, using sigma sub 0 for the strength and r for the pellet radius, I find the force to be sigma sub 0 times pi times r squared Newton. And then the total energy required is the force multiplied with the length. I omit the inlet section for the moment, but just wait. So now we know the necessary absolute minimum amount of energy, and we may readily compute the mass of the pellet produced. So we may obtain a simple expression for the absolute minimum of the specific energy, namely the structural strength divided by the pellet density. The value just obtained is an absolute minimum based on a one-dimensional compression. In reality, there will be shearing, three-dimensional compaction because of the conical inlet section, and, as I already mentioned, will the force in reality be bigger, rather some 700 bar than 500. So let us first double the value to adapt to reality, and then double again to take redundant work and three-dimensional loads into account. And now for the heating. The pellet consists basically of two materials with different properties. One is the dry substance, and the other one is water. The moisture content, F sub W, shall be given on a wet basis, and the two values shall be added together. Let's manipulate the first part of the equations a little bit before choosing values. For water, we used a rounded value 4,200 joules per kilo and degree. Organic materials like wood will typically have CP values about 1,500 to 2,000 joules per kilo and degree. So let us pick 1,700. We now have the roughest equation for the total energy demand to produce pellets. So let's try to compare it with realistic values. We already had that the structural strength was about 50 megapascals, and pellet solid densities are typically about 1,100 kilos per cubic meter. The moisture content is usually about 10% wet basis. The exit temperature from a pellet mill is typically about 120 degrees, and setting the inlet temperature to 20, we arrive at a temperature increase at 100 degrees. With these numbers, we arrive at a bit less than 400 kilojoules per kilo, which is about 2% of the energy normally contained in 1 kilo of pellets. This value is based on the assumption that the material moisture content is the desired value, about 10%, already from the beginning. Depending on handling, on storage of the raw material and a lot of other factors, may there be a need to dry the raw material prior to pelletizing. Force drying is a very energy-consuming process because the vaporization energy for water is 2.4 megajoules per kilo. So, just as an example, will a drying from 30 to 10% moisture content almost use 50% more energy than the pelletization itself. Let's now compare the values we have obtained to reality. In the list of external links with this nugget, you will find one to the Swedish Environmental Research Institute, IVL. The subject of that report is life cycle assessments and energy requirements of Swedish pellet industry. The report is from 2009, but the conclusions and the data are still valid. Table 1 in that report will give you numbers for pellet production from roundwood materials, from wet raw materials, and from dry material. The energy consumption is split in fuel and electricity. For roundwood, wet roundwood, there is a fuel consumption for drying and electricity consumption for chipping and for pelletizing. For wet material, there is a fuel consumption for drying and electricity for pelletizing. And for the dry material, there is only electricity consumption for pelletizing. Scan the report so that you get an idea of how pellet production can be organized and integrated with different types of activity to make it most efficient. As you have now understood, are there two major factors to determine the total cost of pelletization. First, there is the type of tree. Different species will have different mechanical properties. And second, it is the organization of the pellet production. Do you use carpentry dry sawdust from a factory? or do you use round wood straight from a felling site? So what you have to do to be able to do an estimate is first to get proper data for the wood species that might be used. To find such data, I would recommend you go to the web page of the American Forest Products Laboratory. You will find the link among the external links with this nugget. Then search for the Wood Handbook, Chapter 5, and look in table 5.3, 5.4 and 5.5. As you will see, are these tables fairly comprehensive, and chances are that you might find the species you are looking for in these tables. So the value for sigma sub 0 can be read from these tables. In analogy with the example we did, I advise you to use the value for compression parallel to the grain or the fiber. As for moisture content, you will have to look around in your own regions, because what I want you to do is to look in your own region and do an estimate for a pellet production facility based on available raw materials and selling the pellets to a local regional customer. You know how to do it. Do not try to estimate the expenses. To do that, you would end up in a guess number game for interest rates, investments, depreciation times, future fuel and electricity prices and such. Just stick to the cost. The cost is how much energy you have to input to produce the pellets.